Hi, my name is Pankaj Jairu. I am doing this screencast for my lab report on the topic Faraday's law. So basically, I'm gonna take a bar magnet, and a coil which has nearly 560 turns, according to the one given by Dr. Reta in our physics lab. So the Faraday's law relates time-varying magnetic field to a Curly electric field, whose path integral around a closed path is not zero but provides an EMF that can drive current. So basically, if I want to write that in terms of physics or mathematics, then it will be like this. So the electric field will be, so my time varying magnetic field is this guy right here, and my Curly electric field is this guy right here. In other words, I can express the Faraday's law in terms of EMF and the rate of change of flux. So EMF is the negative rate of change of flux, or negative time rate of change of flux. And this n right here is the number of turns of the coil, which in this case is gonna be 560 turns. If I want to do my further calculations, so it's gonna be 560 turns. So in this lab, so after going through every experimental setup, then what we see here is, so basically we want to check two aspects, the qualitative aspect and the quantitative aspect of Faraday's law. So first we want to go through the qualitative aspect. So basically what happens is, now this bar magnet is brought closer to the magnet, which closer to the coil, which is further connected to the computer, and which already has which is connected to the current in other ways. And what happens is, this bar magnet is brought closer to the coil with its north pole facing towards one end of the coil, and on the next step it is the south pole which is brought closer to another end of the coil. And then we want to do it by varying the speed through which this bar magnet is brought closer to the coil. So we want to observe that, and what the computer does is, the software, it gives us the graph between the magnetic field and the time, the rate of change of flux and the time. So basically we want to see the relation between d phi over dt versus the time, and on the first chance it gave us some graph. So I can't pull that graph out. What the graph gave is, it gave me something like this, where this guy goes to the y-axis and we have time in the x-axis, and the graph came out to be somewhere like this. It went down and then it went up, then it went down. Similarly, it decreased, it went down, it went up like this. I mean, in the same way it kept on decreasing. Well, the reason it's doing that is, it's the magnetic field, the rate of change of flux is decreasing. So that's the reason the graph is coming out like that. So from the graph we observed various aspects of that. So in our graph we identified an instant where the magnet was stationary. The magnet was stationary in this phase, because in this time no movement is being done. The instant when the magnet was moving fastest was this instant or this instant, depending upon whether the magnet was brought towards the coil or away from the coil. The next thing was we want to see the relationship between negative dB over dt, whether it's okay or not, and our graph gave us good values in that case. Next thing we're going to see is the quantitative prediction of EMF. The prediction to predict the magnitude of the EMF of the coil, and we need to calculate the rate of change of magnetic flux through all turns of the coil due to rapid motion of the magnet. So we want to determine the magnetic dipole moment of the bar magnet. So what happens is, next thing is, we want to see the negative rate of change of flux with time. So let's say we got the value to be basically the value was 10 to the negative 6 volt from the graph, then actually we can say that it's the rate of change of magnetic flux through one turn of the coil, but we have like 560 turns, so basically the EMF is gonna be negative 560 times, oh my bad, I don't mean to say these turns are negative, but this guy right here is gonna be the negative one. If I take this guy, negative 10 to the sorry, this guy right there is gonna be the 10 to the negative 6 volts. So we figured out what's the EMF on the whole coil. So we did another quantitative measurement in which we saw that we moved the bar magnet 4 times as far from the center of the coil. So this is the center of the coil. We moved the bar magnet, this is 1 time, 2, 3, 4 times, I mean as far as 4 times. Then we saw that the magnetic field at the center of the coil decreased, and it decreased by let's say 1/64th of the original value. So the approximate final magnetic flux through a center of the coil would be given by this formula right here, where we have the number of coils to be same, we have the EMF, and then finally we want to see the estimated EMF of the whole coil. So finally the estimated EMF of the whole coil is this guy right here, my bad, I mean to say this whole guy right here. So so the motive of this screencast is satisfied. We got the meaning of what the definition of Faraday's law is. Next thing we found out the qualitative meaning of Faraday's law. We found out the quantitative meaning of quantitative values of the EMF, which is the quantitative study of the Faraday's law. Thank you, Dr. Allen, for watching to this video. Thank you so much. Bye.